Thanks for having me here. So today I'm going to talk about quantum measurements and how we can try to understand them in an operational way in terms of protocols. It's a different way of decomposing measurements. And this is something that Andreas Winter thought about 10 years ago, and we've extended some of his thoughts in non-trivial ways, so I'll talk about that as well today. This is joint with Patrick Hayden at McGill and Francesco Buscemi and Min-Siu Shea. Okay, so a quick overview. I'm going to start by reviewing Andreas's measurement compression protocol. Maybe that's what he looked like 10 years ago, I don't know. So that's a picture I found on Google. And then I'll talk about our new variation of this measurement compression protocol. And I'll get along to a protocol known as classical data compression with quantum side information. And that will bring us naturally to a protocol that we'll discuss called measurement compression with quantum side information. Okay. And then I'll talk about some applications of this latter protocol. So just to start from the beginning, we all know this, but a quantum state is a positive unit trace operator on some Hilbert space. And a measurement, we model, most generally, we can think of it as a quantum to classical channel, and this is a positive operator valued measure if we're not concerned with the post-measurement quantum state, just with the classical outcome of the measurement. And a POVM, for short, is a collection of positive operators that sum to the identity. And for all the classical outcomes, each of these operators is positive. So the Born rule tells us that the probability of getting a particular measurement outcome, x, from this measurement is given by the trace of a particular operator, lambda x, against the state rho that we're measuring. Okay, and graphically, we may depict this in this way. So this thin line denotes a quantum state. This is a box denoting the measurement, and the thick line is a classical outcome of the measurement, some random variable x. Okay, so now let's start thinking about how to decompose POVMs in a different way. And we know that density operators are in some sense noisy versions of quantum states. I can think of it as a mixture of pure states. And in a similar sense, we might think of POVMs as noisy versions of measurements. Okay, and so what I mean by this is that we may take a POVM lambda and consider it, decomposing it according to a random selection of some other measurement, and then taking the outcome of that measurement and post-processing it with some classical channel, P of x given W. So an arbitrary positive operator may have a decomposition in this form. So the M variable is like, flipping a coin and selecting a measurement at random. The measurement would then be this operator gamma W, and then finally the post-processing classical channel. Okay, so pictorially, we can sort of look inside the box of the previous slide, and in is coming the quantum state rho. This variable M represents the coin flip, choosing the measurement. We perform the measurement, gamma M conditional on the outcome of the coin flip. Out comes some classical variable W, which we then post-process to give X. Now, not all POVMs may have a decomposition of this form, but it could be possible to decompose them in this way. Okay. So now the main question we're going to be asking is, what are the costs of simulating a measurement in a communication sense? Question.
So just like, mixed states can always be expressed as a complex combination of pure states, and that's actually non-unique. There's lots of ways to do it.
Right.
Is there some is it interesting to consider a situation where you have some maximally fine-grained measurements like PVMs, and you ask which POVMs can be decomposed in this way?
Yes, we can consider things like this.
That's all known, or?
A lot of this is characterized, but I'll start addressing some of this in the talk.
Okay.
Okay, so a simple example, these operators right here, they form a POVM. If I sum these two, I get the identity divided by 2, and if I sum these two, I also get the identity divided by 2. If I sum them together, I get the identity. So this is a legitimate POVM, and it's a simple example of how we can think of the simulation idea. Okay, so the decomposition from the previous slide, for this example, one way to decompose would be in this way. So we would flip a coin, choose a Pauli X or a Pauli Z measurement based on the outcome of that coin flip, and then perform the corresponding measurement. Okay, so the idea of simulation is if there's some state that Alice has on which she wants to simulate the measurement, we assume that Alice and Bob can have access to the outcome of a shared coin flip, some common randomness, shared randomness, before communication begins. So in this case, it would just be the outcome of a shared coin flip that picks the Pauli X or the Pauli Z measurement. Alice would then perform the measurement. She'll get some one-bit outcome from that measurement. She sends it along to Bob, and then Bob, using his share of the common randomness and the bit that Alice sent, he can figure out which one of these 4 outcomes of the measurement it was. Okay, and the idea of simulation is that we're using this common randomness to help in the simulation, which is sort of an external source of noise, and in a communication-theoretic sense, it's a weaker resource than classical communication, because I can use a classical bit channel to simulate a common randomness bit, but I can't do the other way around. Okay, so in some sense, this simulation is cheaper than if Alice were to send the 2 bits to Bob that would correspond to the particular measurement outcome. Okay, you can break up the bits and divide them according to common randomness in classical communication. Okay, so now a more interesting example that we could call the Pentagon states. I think Andreas called them the Chrysler states. So the idea is, if we have the block sphere for a qubit, take some slice of it through the center, okay, and along the edge of that slice, we can consider quantum states that form a pentagon, right? And if I sum all of these quantum states, the density operators corresponding to them, they'll sum to the identity. So if I rescale these pure states, then I have a legitimate POVM, okay? And so we can break up this in a simple sort of geometric fashion in this other way, where we think of, choosing a measurement according to common randomness, and then having the measurement outcome sent to Bob. Okay, so for this example, I can take 3 states whose triangle, when you draw the triangle between them, they include the center of this circle, which is the identity operator, the maximally mixed state. I can rescale them so that these 3 states would form a legitimate POVM. I can do the same for any 3 states that include the center, and there are 5 possibilities. So the way that I would simulate this measurement is that I would pick which of these 5 measurements I'd like to do randomly according to common randomness, and then I get one of 3 possibilities, and so that's what Alice sends along to Bob, the outcomes. And then Bob, using all the information from the common randomness and the outcome that he receives from Alice, can put together what the outcome of this original measurement would be. So this forms a non-trivial simulation of the original measurement. Okay. So now we'll get on to the more general case of measurement compression and what the idea is behind this protocol. So we're going to go to the IID setting, the independent and identically distributed setting, where Alice has many copies of the same state, say some state rho, okay? And ideally, the measurement that they'd like to do is a product measurement, the same measurement according to some POVM lambda on each of the states, on each of the copies of the states. From this ideal measurement, there'll be a classical sequence. Each of these measurements gives a classical output, and so there'll be a classical sequence corresponding to all of the measurement outcomes. Alice then sends this, ideally, what she would do is just send these to Bob, okay? But what we'd like to do is simulate this in the way that I was talking about before, okay? And generally, this state will be a mixed state that we can purify to some reference system. And the idea will be to have the state between these classical outputs here for Bob and the reference to be preserved, sorry, not preserved, but the correlations that would be there in an ideal measurement will be the same for a simulated measurement. Okay, so now we'll get on to the next slide of how the simulation would work. Okay, so we're assuming that Alice and Bob share some common randomness before communication begins. Alice uses a particular value of the common randomness to select some other collective measurement, and this is supposed to simulate the product measurement, okay? And from that, Alice will get some outcome L that she'll pass along to Bob, and then Bob, using L and M, will produce this sort of estimate X, okay? And the key idea is for the simulation to be faithful, okay? And so what this means is that the action of the ideal measurement on this tensor power state, including the reference system, should be indistinguishable from the simulated measurement, okay?
So do you really mean indistinguishable? Oh, okay, there's epsilons. That's what I was
Sorry, yeah, approximately indistinguishable in this limit where n is becoming large. Okay, so it's this asymptotic limit. So we can write to the ideal measurement, we can write some measurement map as a quantum to classical channel. So it's accepting some quantum input sigma on the tensor product Hilbert space. It's performing this ideal measurement would have a decomposition. Each of these operators in the ideal measurement would be a tensor product operator. Okay. And in the simulated measurement, each of these could be decomposed as we wrote before, right? So there would be a random choice of the common randomness variable, and conditional on that, there would be some measurement performed, some collective measurement. I'll talk about how the actual protocol works in a bit. And then there would be some classical post-processing, okay? And so the idea is that the true measurement acting on the purified state, where it's acting on Alice's part of the purified state, should be indistinguishable from this simulation process, okay? So any questions at this point? Okay. So now the statement of the theorem is that we'll get sort of a region of rate pairs that are achievable corresponding to classical communication rates and common randomness consumption rates, okay? And the statement of the theorem, I'll draw a picture of this region on the next slide so you can see what it looks like. But these information quantities, the mutual information, just if you don't know it.
Sorry, I'm guessing the R in parentheses is supposed to be the reference system.
Yes, sorry for this.
The
R is the classical communication rate. The S is the common randomness consumption rate. And this R inside is for the reference system. So, sorry about that. Okay, but the mutual information is this linear sum of von Neumann entropies evaluated on this state in equation 1. Okay, so this is This object here is the post-measurement state on the reference, and the outcome of the measurement is placed in a classical register. Okay, and so the information quantities here are evaluated with respect to this state. This was Andreas's original theorem, but formulated in a communication-theoretic sense. Okay. One thing that I'll note is that this theorem holds for what's called a feedback simulation. And this means that Alice gets the classical outcome X from the measurement. She gets the XN sequence from the measurement in addition to Bob. Okay, so this is called historically feedback. I don't know if I like that name, but this is what we'll call it. Okay, so it's just that Alice gets the outcome and Bob gets the outcome as well. It turns out that you'll get a non-trivial trade-off if Alice doesn't have to get the outcome of the measurement. Question?
This lambda is your original measurement, not the simulation.
This is the original measurement, yes. Okay. So interestingly, from a historical perspective, this quantity was identified by a physicist named Grunewald back in 1971, and he called it the information gain of a measurement. Okay. And of course, this is the Shannon entropy. And intuitively, the classical communication and common randomness for this feedback simulation should be at least as large as the Shannon entropy in order for the simulation to be faithful, okay? In order for this, the distribution P of X to be faithfully simulated. Okay, so now a plot of this region, there are some important rate pairs to consider. The first I'll point to, okay, so first of all, this vertical axis is classical communication rate, and this horizontal axis is common randomness rate consumption. Okay, and so this point right here, when there's no common randomness available, in the case that Alice and Bob both get the outcome of the simulated measurement, this point right here is just the Shannon entropy as we saw before. And then to get these points, I just combine with a protocol that takes a classical channel and produces common randomness from it. Okay, so I'll get all these rate pairs along this line with that protocol. So this would really just be Shannon compression. Okay, there's no need to think about anything fancy in terms of measurement compression. This rate pair right here corresponds to Andreas's protocol. This is the Grunewald information gain that we saw, and this is a von Neumann conditional entropy. Okay, and in a sense, all these rate pairs here are a bit wasteful, because you're using more common randomness than you would need in order to simulate the measurement. Okay? So that's the content of Andreas's theorem. So the achievability part of this theorem, we're really just concerned with getting that rate pair that I showed you right here. I suppose I should tell you how you get all these points here. This is just by a time-sharing strategy, where for some of the time you use Andreas's protocol, for some of the time you use Shannon's protocol for Shannon compression, and you'll get the convex combination of all these points with a time-sharing strategy. Okay, so what we're really interested in showing for the purpose of this measurement compression theorem is the achievability of Andreas's protocol. Okay, and so that we can write as this resource inequality and this resource formalism that Devitak, Harrow, and Winter established in 2005. And the idea is that using this rate of classical communication, this rate of common randomness consumption, we can simulate the action of the ideal POVM lambda on the state rho. Okay. So now to think about achievability, I want to think about a particular ensemble corresponding to the measurement operators and the state on which you want to simulate the measurement. Okay, so this distribution P of X we saw before on the first slide, this is just the probability for the classical outcomes. This state right here, you can show will be the state of the reference system if you perform the measurement on Alice. There should be a transpose there, but it isn't really that important for the purposes of what we're doing. Okay, but in a sense, the measurement performed in Alice's system will induce this ensemble on the reference system. Okay, and we can start thinking that the goal of this protocol is to steer the reference using quantum steering to be an ensemble of this form, okay? And the way that you can do this steering is with a square root measurement constructed from this ensemble, and you can calculate that the average state of this ensemble is the state rho. I can do that for you quickly. So the average state should just be P of x, rho of x, right? So then the P of x will cancel right here, and I'll just be left with this condition. Then I can bring this sum inside, and from the fact that this is a POVM, this average will be the state rho, okay? So if we're thinking that the objective is steering, this is really the measurement that's performed on the reference system, okay? And then we start thinking, well, how can we do this approximately, okay? And we start using Shannon theoretic ideas of random selection, okay? So the idea ends up being, we'll have some set L corresponding to the classical messages that Alice sends over the channel. There'll be some set M, which are indices for the common randomness, okay? And so this set L, its size should be exponential in this rate for communication, and the set M should be exponential in the rate that we gave before, okay? And so what you do is you select this number of code words, the product of the set sizes, according to the IID version of the distribution P of x that we had for the measurement, okay? And these code words will be indexed by the classical communication indices and the common randomness indices, okay? And then the first idea is to exploit this Alsviti-Winter operator Chernoff bound to guarantee that the sum, the sample average of density operators constructed from these code words will be approximately equal to the average, the true expectation. So if I were to take, just as I showed you here before, if I were to take the nth extension of this formula, right, this would give me the true expectation of this ensemble that we're randomly selecting from. And when you just evaluate everything, you can show that the average is rho tensor n. So the operator Chernoff bound is a statement of convergence, how this operator sample mean is converging to the true expectation, okay? And then if we have that this condition is true, we can build up a POVM that's similar to that steering POVM I showed you on the previous slide. Okay, so I'll take rho tensor n, 1 over L. I'll take these quantum states that are conditional on the code words selected. And this is what we'll call, I'll call it upsilon m sub L. So it means that the common randomness is selecting this particular measurement with outcomes L, okay? And if this condition is true, then you can see, using a similar thing that we did before, if I were to sum over these operators, you can take this inside. If this is approximately equal to, oh, I'm sorry, this should be a -1 here, like the steering ensemble that we had before. Sorry about that. So if I take this inside, this is the square root measurement. Yeah, but it's sort of an approximate version of it. Okay, and so these will cancel, right? And we'll just get the identity operator. So that's the rough idea of what's going on. So we're trying to think what's the minimal number of classical communication code words and common randomness that we'll need to have this condition to be true for every value of the common randomness. And if this set is approximately this size, then we can guarantee that this condition is true from the operator Chernoff bound. Okay, so this first condition that I showed you is helpful for constructing a POVM of this form. And then the second condition is to guarantee that an empirical distribution, if I consider all the code words, these XNLMs, I want the number of them to be, for a particular XN, to be approximately equal to the distribution, the IID distribution, PXN. Okay, so I want another type of convergence statement that this empirical distribution for the code book is close in variational distance to the true distribution. And with these two things, Andreas showed that you can have POVMs and that the simulation will be faithful according to the criterion we showed. Okay. So that was the achievability part of the theorem. What's also nice for this theorem is that it's what we call single letter. Okay, and it means that the rates that I showed you in the theorem are the optimal rates. Anything outside that region will not be achievable in this faithful simulation sense that I showed you. Okay, and single letter means that these entropic formulas need to be evaluated with respect to one instance of the state and the measurement, so that classical quantum state that I showed you in the statement of the theorem. Okay, and this type of result is really the result that you're looking for as an information theorist, because it sort of tells you that there's nothing much else to look for in this theorem. That the problem is solved from an information-theoretic perspective. And this type of result happens more often in quantum information theory when the resources are of a somewhat hybrid nature, if they're classical and quantum resources. So I guess I think that's why this is holding in this case. And the main steps for the converse are just thinking about that first picture that I showed you of the most general protocol for a measurement simulation, how it would operate. And then if I just exploit the quantum data processing inequality several times, you can prove this result. So it's not that hard to show. Andreas actually proved what's called a strong converse, meaning that if you're outside the region, the simulation will become exponentially bad as n becomes large. So it's a stronger statement than this statement here. Okay. So now we'll move on to this new stuff that we're looking at.
Sorry, I have well, maybe a long question, but I'll say it anyway.
Okay.
We'll discuss it later. Is it, I mean, the protocol that you talked about, Andreas' protocol uses some sophisticated quantum measurement, but is that really necessary? I mean, Alice is it's supposed to be just a regular measurement. She gets some classical bits. They have imperfect correlation with the reference system, and she wants to send them just classical bits to Bob so that this imperfect correlation is preserved. That seems like a classical protocol.
Right, but you're trying to minimize the amount of classical communication needed.
Yeah, but the answer is just the mutual information, right? I mean, it seems like Alice could do privacy amplification to separate out the information that the reference system knows from the stuff the reference system doesn't know, compress and that's the mutual information there, right? And compress that part, and then Bob.
There could be other ways of proving this theorem.
Okay. Okay.
So, but I guess I was just presenting Andreas and the way that he thought about it. But I guess this was 10 years ago. So.
Okay.
Okay. So in the non-feedback measurement compression, this is the scenario where Alice doesn't necessarily need to get the classical outcome xn from the measurement, right? The previous protocol I was showing actually demanded that, okay? So now we suppose that these measurement operators can be decomposed in this form, okay, where I can think that there's some POVM consisted of operators MW being performed, and then the classical outputs W are being post-processed by some classical channel, okay? And what we could do then is to simulate this measurement MW first, and then Bob could locally simulate this post-processing channel, okay? And in general, the classical communication cost will be larger if you do this because of the data processing inequality. Right? If I consider this information quantity, which will correspond to the measurement of MW, since W gets post-processed to produce X, this will be larger, okay? But the benefit of doing this, okay, is there a benefit of doing so? Yes, there is that the common randomness cost can be lower, okay, because Bob can simulate X from W. And if the common randomness cost is low enough such that the total cost of classical communication and common randomness consumption is lower than the Shannon entropy, which was the total cost from before, then we've gained something, right? If the total cost is lower, okay? So again, the picture is like we drew it before. I guess I didn't draw before the xn going to Alice, but this time the protocol operates similarly. There's many copies of the state row for Alice. The measurement gets, the simulation for MW gets selected according to the common randomness. The outcome L gets sent to Bob, and then Bob locally processes. From this, he could reconstruct a WN code word, okay, for the measurement MW, and then he could post-process that to produce XN, which is the simulated measurement outcome. Okay? So the statement of achievability is slightly different from what we had before. This information quantity ends up being the relevant quantity for classical communication because you're simulating the outcome W of this intermediate measurement. The common randomness cost can be lower than it was before. Okay? And again, this is because Bob is going to simulate this post-processing locally. Okay. So the total cost, if you combine these together with the chain rule for mutual information, will be this amount, which can be lower than the Shannon entropy. Okay. And what's nice in this case, maybe it's a surprise, maybe it's not, we're able to prove a single-letter converse in this case by extending a technique of Paul Cuff, who's an information theorist at Princeton. We adapted his technique to the quantum case. He was considering simulating classical channels in a non-feedback way. Okay, and using some of the ideas in his converse, we could prove a single-letter converse. Okay, so the statement of the theorem is a bit more complicated. I apologize for that. But in this case, most generally, we can think of a quantum instrument that's being performed on the state row. This is the most general map with a classical outcome and a quantum output as well. Okay, so each of these operators, NX, or these are maps that are completely positive, trace non-increasing maps. And then if you get the outcome X, you place that in a classical register. So we think about all the ways that we can decompose these maps, NX, into maps of this form, where we have some trace-reducing maps, MW, and then some classical post-processing. So we think about all the ways we can decompose this and evaluate these information quantities with respect to this state right here, which captures sort of everything that's going on. We have the post-measurement state for the reference when outcome W is obtained. This W gets put in a classical register, and it gets processed to produce the classical outcome X. Okay, so if I were to trace over the W register of this state right here, I would get this state. Okay. And so the statement of the theorem is that we take the union of these regions that we had before over all possible decompositions of this form. Okay. And so to give you an idea of what this, the idea is that the total cost can be lower, and you can have a non-trivial trade-off between classical communication and common randomness consumption if you do this. So this is a plot that yeah.
What was MW is another instrument or an instrument with some
It's
property?
you can think of it as another instrument. So if I ignore X here, this is, I have an instrument, this MW. These are the trace-reducing maps, and then the classical outcomes get placed in W.
So without particular assumptions on like linear and extreme point? Or
Without particular assumptions, yeah. So yeah, you might want to do some further optimization over the maps that you have to consider in this decomposition in order to make, if you actually wanted to compute this region, you might want to do something like that. Okay, so this is a picture that I stole from the quantum reverse Shannon Theorem paper. It suffices to illustrate the idea of what we're thinking about. Okay, so this plot is for a classical channel simulation. I can consider this to be a special case of measurement compression, right? If I have the state rho and I think about its spectral decomposition, I could then do a measurement in that eigenbasis that dephases and stochastically produces some classical outcome. And this would be a classical channel, right? So this plot that was featured in this paper suffices to illustrate the idea of non-feedback simulation. Okay, so the simulation with feedback is this region over here that I was showing you before, where there's not a trade-off, right? But then if you start considering decompositions of the measurement, you can have a non-trivial trade-off. And in particular, even if there's no common randomness, the simulation cost can be quite a bit cheaper. Okay?
Is this a specific channel, or is that just a schematic?
This was a schematic, yeah. Sorry about that. Okay. So now I'm going to talk about this protocol, classical compression with quantum side information, and then this will lead us to the new protocol, measurement compression with quantum side information. Okay. Because we'll be using ideas from Andreas's protocol and this protocol in order to stitch together protocol for measurement compression with quantum side information. Okay. So I should say that this, I'll call it CDC-QSI, was established by Devitak and Winter about 10 years ago. And the main idea for this protocol is that there's some ensemble. Okay, say the states rho of x are selected according to a distribution p of x. Okay. And an information source generates some classical sequence according to the IID version of this distribution. And conditional on that, it prepares some quantum state rho xn. The notation is implicitly that this is a tensor product state. Okay. So the information source produces the classical sequence in the quantum state conditional on that classical sequence. It sends the classical sequence to Alice, okay, and then it sends the quantum state to Bob. And the information-theoretic question is, how much classical communication is required for Alice to send to Bob such that he can recover the classical sequence xn, okay? And one idea that's naive is to just Shannon compress the sequence xn to the entropy h of x for this distribution. But our intuition is that we should be able to do better with this quantum side information. Okay, so again, the ideal protocol is that the sequence x1 through xn gets sent to Alice, Bob gets these, and we want it so that the state that Bob has is approximately equal to the state of this classical system in these quantum states. Okay?
Can Bob destroy the quantum state?
That's not allowed. The state should be approximately the same in the asymptotic limit. So this is an important point in the protocol. Okay? So the way the actual protocol will work is that the source gives some sequence to Alice, and then she performs a hash of this sequence. And you can think of a hash as just that. Oops. No. Oh, that one doesn't work. Okay, sorry. So a hash is just that we have these different bins, right, with some indices, 1, 2, through some big L, okay? And the sequences just get thrown into these little bins, okay? And then what Alice ends up sending is the index of the bin, okay? So Alice sends the index of the bin, and then conditional on that, Bob has to perform some measurement on his quantum states, his quantum side information, to try to deduce what the classical sequence that Alice got, the classical sequence that Alice received from the source. Okay, so the two steps are that Alice hashes the sequence, sends Bob the hash, and then Bob has to perform some delicate measurement, conditional on the hash value to recover the sequence xn. Okay, and the statement of the theorem for this setting, it's also a single letter theorem. If we consider a classical quantum state that's isomorphic to the ensemble, P of x, rho of x, this sort of characterizes the information source. And the lowest rate of communication is the conditional von Neumann entropy evaluated on this state. Okay? And the intuition for why this should be the rate is that from Shannon compression, we know to represent the sequence coming out from the source, there's approximately a number of bits that's linear in the Shannon entropy needed to describe that sequence. Okay? And then from the Halevo-Schumacher-Westmoreland theorem of quantum information theory, Bob should be able to recover a number of bits that's linear in the Halevo information of this ensemble by measuring his quantum state that's conditional on this classical sequence. So this is the number of bits that he should be able to learn about the sequence xn. And then what Alice should have to send is just the difference of these amounts so that he can have a complete description of this sequence. Okay? And the way that we proved...
Excuse me.
Yeah.
So you said the state should remain unchanged at the limit?
Yeah.
But
in the asymptotic
your
limit.
argument also works if you are allowed to... this argument also works if you are allowed to change it, to destroy the state.
Yes, but okay, so I guess you can consider it a bonus of the protocol that it won't disturb the state as well.
So do you lose anything by this constraint?
No. No, this is the optimal rate. So I guess it's a nice feature. And this ends up being crucial in our protocol for measurement compression with quantum side information. That shouldn't disturb the state. So the statement of achievability is, again, we can phrase it in this resource inequality formalism. So here's a resource that Alice and Bob share before communication begins. It's many instances of that ensemble or a classical quantum state corresponding to that ensemble, combined with this resource and this rate of classical communication, they can generate a state where Bob has a copy of the classical sequence. Okay, so it's just the statement that Bob can recover the sequence xn. Okay, and so the strategy that we use to prove this is exactly like this old classical protocol from the 1970s of Slepping and Wolf. So the way that this works is before communication, Alice throws the typical sequence randomly into different bins, okay? And she's just concerned with the typical sequences because this is where all the probability mass is, okay? And the atypical set doesn't have any mass. So, she throws the sequence, she goes through all the typical sequences and throws them into bins randomly, okay? And after doing this, there's some assignment of the sequences to bins, okay? But this was done randomly, okay? But after it's done, it's known. And part of the assumption is that Alice and Bob are allowed to meet beforehand to agree upon a strategy, okay? So that Bob knows the assignments, and then they go their separate ways, and the source generates some sequence randomly, and the protocol has to work, okay? So how this will work is that if the source generates the sequence xn, there will be some assignment to a bin, okay? So suppose that it assigns the sequence to this bin, okay? Then Alice sends the bin index to Bob, okay? So he has that classical data, and he knows how the code was chosen, right? This is assumed. And so he knows all the sequences that are in this bin, okay? And to each of these sequences, there's a quantum state assigned. There's a quantum state on his side, okay? So for the actual sequence that was sent, there's some quantum state rho xn. It's conditional in that sequence. And there are other quantum states, say rho x prime and rho x prime double prime n. And what he does is he performs binary measurements, asking, is my state this state? And he'll get an outcome yes or no. Is my state this state? He'll get an outcome yes or no. And what we like is that when he's scanning along, he gets no, 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 until he gets to the actual sequence. He should get a yes, okay? And we can guarantee that as long as the number of bins is approximately this size, the scheme will work, okay? And so this idea of sequential scanning is related to some advances in sequential decoding for classical communication over quantum channels that have come about in the past 2 years, I guess. Okay, so that's the idea behind the protocol. I'm not going to prove to you that it works. We'll have a paper coming out at some point. Okay, the converse. I guess I wrote it out for you, but the main step is to think about, or the main idea is to think about the most general protocol. And at this step, so we do some entropy things, some inequalities. And at this step, we're applying quantum data processing from the bin index L and Bob's quantum state. He gets some approximation of the sequence that the source generated, okay? And assuming that the protocol, in the converse part of the proof, you assume that the protocol is good, and so this conditional entropy should be low. And anyway, I want to talk about measuring compression with quantum side information, so I'll skip this converse, talking about it in detail. Okay, so now this is sort of the final part. Measurement compression with quantum side information is a natural extension of 2 of the previous protocols that we saw, right? So now we're assuming that Alice and Bob share many copies of some state, rho AB. This state could be entangled, it could be separable, whatever. And in the ideal protocol, we want it so that Alice is performing the same measurement, this product measurement, and Bob gets the classical outcome. Okay, so the actual protocol, the diagram, will look somewhat like a hybrid of what we saw in the previous 2 protocols. We let Alice and Bob share some common randomness. Alice selects a collective measurement according to this common randomness. She gets some outcome L. She hashes L according to some hash function. Bob, conditional on the common randomness and the hash that he receives from Alice, performs some measurement on his systems using the quantum side information to recover this approximate classical sequence. And this whole process should be that the state on the reference, these classical registers, and Bob's quantum registers should be approximately equal to the state in this ideal protocol, the results from this ideal protocol. Okay, so what's important here is that these states can't get disturbed. I mean, the disturbance has to be negligible in the asymptotic limit. Okay, so the statement of achievability, it gets more complicated, but the resource shared at the beginning is this state rho AB, it's this non-local resource. The classical communication required is similar to what we saw before. If there's no system B, then it's the same as what we saw in Andreas' protocol. But if there's B available as quantum side information, these rates are lower, right? So there's not as much cost required because Bob can make use of this quantum side information. So, and this is a conditional quantum mutual information. This is the rate of common randomness consumption, and the protocol should be that the measurement lambda is simulated on Alice's system. Okay, the proof strategy, it's not just a straightforward concatenation of the two protocols of measurement compression and classical compression with quantum side information. The reason is that we had these code words for measurement compression that correspond to the measurement that's chosen. And those code words need to be synchronized with the code words that Bob is using. There'll be some conditional states on Bob's side from the measurement simulation, and those, the classical sequences corresponding to those conditional states should be synchronized with the code book for measurement compression. So there's an argument that needs to be made, and we made that. The idea behind the protocol is to do a similar thing to measurement compression, choose a hash function randomly, and the way that it works is that, the way that it actually works, it ends up being sort of a hybrid of the protocols. Alice performs the simulated measurement, hashes the outcome, sends it to Bob. Bob gets the hash. So now we're doing something that's similar to classical data compression with quantum side information. And then he performs these binary searches that we were talking about before. There will be post-measurement states on his side that are consistent with the hash that he received. Okay, and so he'll scan over all those post-measurement states using binary projective measurements. Okay, until he gets a yes from one of those measurements saying that his quantum state is consistent with the hash. Okay. So the statement of the theorem in the feedback case where Alice gets a copy of the measurement outcome as well is similar to the statement of Andreas' theorem, but the information quantities are conditional on this quantum side information. Okay. And the converse is also single letter. We can prove that. And the steps are thinking about a general protocol for this task. The fact that the states on Bob's side cannot be disturbed, that's also important in the converse. And then exploiting the quantum data processing inequality. Okay. So I hit an hour, and I think, isn't the time limit 1 hour for this seminar?
You can go 5 more minutes. We still
5 more
have
minutes?
5 minutes.
Okay. So I'll talk about the second application of this measurement compression with quantum side information protocol. Okay, and it's a new quantum reverse Shannon theorem for an instrument. Okay, so we'll skip over this. Okay, so we have a reverse Shannon theorem for channels. This was done by 2 different groups over different time scales. And so the idea of the reverse Shannon theorem is you want to use quantum communication in, say, entanglement to simulate a channel, okay? And this may seem like a strange task, but it's useful for proving strong converses for capacity theorems, saying that the capacity is really like a hard limit, where if you're above capacity, then the error goes exponentially to 1, whereas if you're below capacity, you can make the error go exponentially to 0. So it's useful for that. It's also useful for lossy data compression. Okay, so these are some of the more down-to-earth applications of the reverse Shannon theorem. Anyway, so we have a reverse Shannon theorem for a quantum channel. We also have one for a POVM. That's what measurement compression is, right? And so then a natural question to think about is, well, what about having a reverse Shannon theorem for a quantum instrument, right? Quantum instrument has a classical output and a quantum output, and you would think that you could use classical resources to simulate the classical output of the instrument, and you could use quantum resources to simulate the quantum output of the instrument, right? And if you're using this hybrid structure, it's cheaper than just using quantum communication and entanglement, because classical communication is cheaper than quantum communication. Okay, so the way that this reverse Shannon theorem works is for a given instrument, so an instrument would be some map, right, from an input A to a quantum output B and a classical output X. And then I could take an isometric extension of this instrument, and it would be of this form. So here I put B prime. Okay, and we're trying to simulate the action of this instrument on many copies of some state rho. Okay, and using a measurement compression step first, followed by the quantum reverse Shannon theorem conditional on those classical values, we can simulate the quantum instrument. So again, this is cheaper than performing a simulation with just quantum resources. And then there's a statement that gets very complicated and than this one, but this is a reverse Shannon theorem for an instrument when the state on which we're simulating is an entangled state, or some bipartite state shared between Alice and Bob, and Alice has simulated the instrument locally. Okay, and so what happens is that many of these entropic quantities, they're conditional on the quantum side information. Okay, so I'll stop there. So in conclusion, this measurement compression protocol, it gives us a way of thinking about quantum measurements in a different way than perhaps the usual way, a nice operational way. What we did in this recent work was to get this further decomposition of a measurement for a non-feedback simulation where Alice doesn't have to get the outcome that Bob does. And then we had this protocol for measurement compression with quantum side information. It has some other applications that I didn't talk about. So what we're doing right now is we're taking the next step. We're thinking about measurement compression with quantum side information, but thinking about the scenario where Alice doesn't have to get the outcome. Okay, so this is the next thing. We have an achievability statement. We have a conjecture for what the theorem should be. It's a natural extension of the non-feedback measurement compression theorem. And we're trying to prove the converse with progress. And a good open question to think about if you're interested in this type of work is to prove the measurement compression theorem such that it works, you're simulating the measurement on an arbitrary state. Okay, so you're trying to simulate the measurement really in the diamond norm of this quantum to classical map. Okay, and this has been done for quantum channels, but the protocol there required entanglement and quantum communication. To do this, it's natural to conjecture that you would, or it's very, very likely that you'll only need classical communication and common randomness to do this. Okay, so thank you very much.
questions?
So Shor's original idea for proving the quantum Reverse Shannon theorem was to combine measurement compression with a kind of noisy teleportation, and to compress the measurement outcomes in the noisy teleportation. So if you play the same game here, say in the full most complicated protocol, like the non-feedback quantum side information, or just say the non-feedback case, do you get an interesting non-feedback quantum Reverse Shannon theorem?
Right. Yeah.
How can the quantum reverse Shannon theorem be anything but non-feedback? Because you're sending quantum information.
In the Reverse Shannon theorem, Alice gets the environment of the channel. So that's what is meant by feedback there.
Okay.
Right. So the way that was done was to think about the Krauss operators of the channel that you're trying to simulate as measurement operators, right? And maybe if those could be further decomposed in terms of classical post-processing, then there would be a gain, perhaps. But then again, these, yeah, I'm not sure. Question?
There's a couple of questions. And the first, probably just naive, they don't know enough quantum Shannon theory, but the analog of the two protocols we discussed with compression, either simulating measurements or simulating a quantum instrument, if you leave all the classical variables out of it and you just have quantum correlations between Alice and Bob, and they're trying to simulate Alice transferring her quantum share over to Bob, that's just quantum state merging. Is that right?
That's state merging, which is like a reverse Shannon theorem.
Okay.
You can think of it in that way.
Good. The second question is, you didn't use the language of sufficient statistics in any of this, but essentially you were asking, like in the measurement compression question, what you need to find for Alice to transfer to Bob is some classical variable which is a sufficient statistic for her outcome, conditioned on the shared classical variable that Alice and Bob have. And it has to be sufficient for the quantum system that's far away.
Right.
And so there's some stuff in Petz's book and elsewhere on quantum sufficient statistics. And I've always found those definitions very confusing, and I've never really sort of sorted it all out. But I'm just wondering whether you think about this quantum instrument stuff as yielding a definition of a quantum sufficient statistic.
Right. So I'm not sure what the answer is. What I do know is that Andreas, he does tackle this question in his paper. And I believe he said that there's a difference between what he's doing and this sufficient statistic idea.
Uh-huh. This is the 2002 paper you mentioned.
Yeah.
So it's not the same as what Petz is doing.
Yeah, I don't think so. But I don't have a good answer for you, so sorry.
In Petz's book, it's all exact, at least.
Right.
Which would be sort of at least a technical difference.
Mm-hmm.
More questions? No? So let's thank Mark again.